Hello everybody, my name is Paras Singh and my roll number is 2K20 ME 182. And for my fluid systems project, I have studied the research paper titled Performance Assessment of Lift-Based Turbine for Small Scale Power Generation in Water Pipelines using Open Foam. And this paper has been published in the Engineering Applications of Computational Fluid Dynamics journal in on 7th Feb 2022. So starting with the paper. As we all know that in today's world of growing energy concern, hydropower is an important source of renewable energy as it is abundant, cheap and predictable as compared to the other energy sources out there. And turbines are used to extract the energy available from water. The energy could be in the form of potential energy of water stored uh, at a higher level compared to the base level, and other one could be the energy that could be extracted from flowing waters in river streams or canals. So power output of these turbines ranges from zero point 0.1 kilowatt to 100 kilowatt, and these power can be extracted as explained earlier with the help of turbine. And to increase the power output even further, an array of turbines can be used, and the application of the power generated from turbine could be numerous, and the power extracted from pipeline systems can be of two types. First one could be from the gravity fed pipelines, and second one could be from pressurized pipelines. And the turbines in pipe can be installed in gravity fed pipelines supplying water from elevated tanks or mountains. And as explained earlier, in these cases, the potential energy of water at a higher level is converted into electrical energy. However, on the other hand, the pressurized systems, the turbine are installed in pipelines that have pressures above the atmospheric pressure, and the higher pressure is used to drive the turbine, which in turn is used to generate the electricity. And these turbines can have diameters that can range from about 82 to 50 millimeters, and the flow velocities can vary from 1.5 to 3 meters per second, and the number of blades could range from about 6 to 20, and the power output can range from about 80 to 40 480 kilowatts 480 watts, sorry. And the pipe turbines in general are classified in two categories. First one would be the horizontal axis turbines, and second one would be the vertical axis turbines. And through the medium of literature review, the author found that the vertical axis turbines have advantages, have various advantages over the horizontal ones, and particularly some of the advantages are like the operating conditions of the incident flow uh, does not affect the performance of these turbines, and in general the vertical axis turbines have higher efficiency at lower speeds compared to the horizontal ones. And uh, and the driving force for these turbines can be of two types. First one is the drag force and second one is the lift force. And in general the author found that the drag based pipelines have various limitations. Particularly they have a lower power coefficient and higher pressure losses associated with the system. Also, the drag based turbines require more blades to have a sufficient buildup of energy to drive the blades. This is due to the higher inertia of the turbines, whereas the lift based turbines can operate really well at lower velocities. And particularly widely used and popular turbine lift based turbine is the Darius one, and these turbines have lower obstructions to the flow than the drag based ones, and they have in general better starting capabilities and a higher power coefficient. So the reason behind which the author conducted this study was that he found that there are not much information available online regarding the performance characteristics of the lift based turbines, lift based water pipeline turbines. So he conducted this study, conducted numerical research on lift based helical turbines, and and we'll be learning the his findings in the later part of my explanation. So the paper is aimed at assessing the performance of these vertical axis turbine to understand the impact of the various parameters on the overall performance of the system, and it is also based on evaluating the effect of the operating conditions, particularly the tip speed ratio and the velocity, and the geometric parameters that affect the pressure drop inside the pipeline. Also, the paper aims to study the impact of the turbine shafts and the hub on the overall performance, as well as the wake generated by these turbines. So, the author in this study, the author has analyzed a turbine that has diameter of 600 millimeters, and for the numerical analysis, the author has used popularly and widely used open source CFD solver called OpenFOAM. And in the solver, the author has analyzed the lift based helical bladed turbine, and he has studied the effect of various parameters, the wakes and all, and he has presented his findings in a very effective manner. The paper starts with a brief explanation of what all theory is required by the reader to understand what a lift based turbine is, followed by the turbulence model that the author has used to conduct his study, and the validation, how he validated his turbulence model, and also the mesh generation and the boundary conditions that have been applied on the turbine. So, starting with what a vertical axis lift based turbine is, as the name suggests, these have their rotating axis of rotation that is perpendicular to the flow of stream, as well as the main driving force for these turbine is the lift force. And as I explained earlier, the Darius wind turbine or Darius water turbine is a very popularly used turbine, and it was the first turbine, a lift-based turbine that was invented for this application. But this turbine has various shortcomings. Particularly, it has a it has a pulsatile torque, and which is not good for the overall turbine efficiency as well as the product life of the turbine. So, for improving the shortcomings, the Gorlov's helical turbine was developed, and in this turbine, the blades were changed from the straight to the helical position, and which decreased the shortcomings of the Darius turbine. And further, the Gorlov helical turbine is generally in cylindrical shape, but to fit this turbine in a pipe, its shape was changed from cylinder to the spherical shape. And this figure represents the Gorlov's helical turbine. Here you can see the blades. Blades are arranged helically, and the blades are attached to the top hub as well as the bottom hub. And this turbine rotates in the pipe. This is the front view. We are looking inside the pipe. So a clearance is left between the blades and the pipe, and generally 3 to 5 blades are there in this turbine. And and the cross section of this turbine is shown here, and we can see, it is a hydrofoil, particularly the Naka 0020 hydrofoil. And through the literature review, author found that this hydrofoil is very efficient in improving the performance of this turbine. And the chord length of the hydrofoil that the author selected for this study was about 15% of the turbine's diameter. The governing principle behind the working of this turbine is that as the turbine blades rotate, the angle of attack of the incoming fluid to the turbine changes at different azimuth angle. Azimuth angle is the angle between the turbine's cross section and the and the horizontal axis. So this azimuth angles varies from 0 to 360 degrees. And as the azimuth angle changes, the angle of attack of the incoming fluid changes, which leads to changing lift force as well as changing drag force. And the magnitude of lift force is greater than the magnitude of drag force, which is the main driving force behind the rotation of this turbine. Here is the velocity triangle for this turbine. Here you can see the velocity vector of the incoming fluid, the peripheral velocity of the turbine blade, and this shows the relative velocity of the incoming fluid, which makes an angle alpha with a tangential direction. And now I'll be explaining you how this turbine solves the shortcoming of Darius turbine, that is of pulsatile torque nature. So in this turbines, the helical angle is the key factor in eliminating this shortcoming. So, what it does is that in this spherical turbine, they have a helical angle of phi, as shown in this diagram, and this angle phi distributes the hydrofoil section evenly during the turbine rotation, and which means that there will always be a hydrofoil section at every possible angle of attack. In this way, the sum of the lift and drag force on each blade does not change abruptly with the rotation angle, generating a smoother torque curve. So there is much less vibration and noise than in the Darius turbine. It also minimizes the stress in the pipe section where the turbine is installed and facilitates self-starting capabilities of the turbine. And here is shown the formula of the efficiency of turbine. So efficiency is basically the ratio of the brake power to the water power. And here all the parameters are self-explanatory. And there are two parameters that govern the performance, that mainly governs the performance of this turbine. First one is the tip speed ratio or the TSR, and second one is the solidity sigma. And solidity is the ratio of the total blade area to the swept area, as shown in equation number two. And the tip speed ratio is basically the ratio between the peripheral velocity of the blade to the velocity of the incoming fluid. The lift-based helical turbine has been analyzed using the OpenFOAM solver, and the governing equations for the simulation is the Uran's equation or the unsteady Reynolds average Navier-Stokes equation. The turbulence model utilized for the simulation was the K omega SST model or the shear stress transport model. This model was used as it is particularly efficient in solving flows involving flow separation and adverse pressure gradients. And through literature review, the author found that this model would be the appropriate one for the simulation, and the flow domain was made as such to remove or reduce the effect of the flow domain on the simulation results. And for that, the inlet and outlet pipe lengths were set as 12 and 10 times the pipe diameter respectively, and the pipe diameter was chosen as 600 millimeter. The turbine model was created using Selom 3D CAD software. Afterwards, it was imported on OpenFOAM, and a block mesh was generated after splitting the domain into three parts. First one was the inlet pipe length, second one was the turbine length, and third one was the outlet length. And the inlet and outlet flow domain was set as fixed, while the turbine flow domain was set as rotating for simulating the effect of rotating turbine. And as explained earlier, the block mesh was generated, which is particularly a good and efficient mesh for discretizing the flow domain, as it leads to better convergence and increases the stability of the overall solution. And for the transient simulation, the time step was kept as variable and with an average of 2 to power minus 5 seconds, and it was implemented using the sliding mesh techniques. And the various number of cell domains were chosen, and then mesh independent study was performed to find out the appropriate cell distribution in the whole domain. And this graph shows the error with the number of cell domains, and it was found that at 4 million mesh size, the error minimizes to an appropriate level, and hence 4 million mesh size is the optimum mesh distribution for the study that the author had done. And after that, he performed various sensitivity analysis for finding the appropriate time step for the study. And the covariant number that he chose was 0.0025, and the simulations were performed, and the overall time for each case was about 12 hours to reach the steady state solution. And the transient case solution for three revolutions of the turbine took an average of 648 hours, that is 27 days, using the specification of the computer mentioned here. And after this, the author validated his turbulence model and the overall model of the simulation using experimental data available online. And for that, he took the experimental data from research paper of two authors, particularly this one and this one. And the results were results are given in this figure, and we can clearly see that the numerical and the experimental results are relating closely, and hence the turbulence model and the overall model that the author has developed on OpenFOAM is appropriate, and can simulate the flow situation properly. Now I'll be discussing the results of the simulation, starting with the generated torque by the turbine. These graphs represent the variation of lift force, drag force, as well as torque at with the azimuth angle at different tip speed ratios and incoming velocity of water in the pipe. And from these graphs, we can conclude that the lift and drag force increase with the turbine revolution and increase in the azimuth angle until a maximum value is reached at theta of 72 degrees, corresponding to an angle of attack of 22 degrees. And at the azimuth angle of 72 degree, the flow starts to separate around the blade, and this can be seen in the pressure contours shown here, pressure and velocity contours. After this, the separation leads to a deterioration in the overall performance of the turbine, and the lift force starts to approach the stall condition. So we can say that the alpha equal to 22 degrees is the critical angle of attack for the turbine blade cross section. And and we can also observe from the graphs that after changing the tip speed ratio from 2 to 4, the stall conditions occur even earlier as compared to the previous case, and this leads to an average blade torque output increase by 150%. After this, will be looking at the flow variation of flow velocities. So an increase in the flow velocity from 1.5 to 3.5 meters per second yielded a torque that is 4.5 times higher than the initial torque, as well as the turbine power reached up to 3600 watts from 400 watt, that is a 9 times increment. And flow velocity although increased the power output, but it also increased the head losses of the turbine, which increased from zero point 0.6 meters to 1.6 meters, that is an increase of 167%. And it should be noted that the turbines, although these turbines have these properties, they also does not obstruct the flow in the pipeline in the stall condition, nor does it induce high pressure losses. And from the figure 7 that is shown here, we can see that the wake of the turbine blades gets diminished after 4 times the pipe diameter. And after this, velocity the velocity distribution gets equal to the fully developed flow. And the simulations showed that the flow velocity increased the turbine efficiency from 18% to a maximum value of 28% at a free stream velocity of 2.5 meters per second. Now coming to the impact of number of blades on the performance of these turbine. So first of all, through the literature review, author found that from the findings of Lucid Energy Technologies that the number of blades in a turbine are restricted to a maximum value of 5, as more greater number of blades cannot be accommodated on the lower and bottom hub of the turbine. So it is basically a design constraint, and hence the number of blades cannot exceed 5. So the author uh, analyzed turbines in having blades ranging from 3, 4, and 5. And here are the graphs of the performance parameters of a 3, 4, and 5 bladed turbine. And from these graphs, we can see that the overall power increases in with the increasing number of blades. The torque gets more uniform for high 5 bladed turbine, and the efficiency also increases with increase in number of blades. But the this graph also shows that although the performance power and the torque gets improved with increasing blades, the head loss also gets increased with the number of blades in a turbine. And these are the pressure and velocity contours for 3, 4, and 5 bladed turbines. The author also investigated the effect of chord lengths on the turbine performance, and for which he increased the chord length from 58 mm to about 87 mm. And the turbine solidity represents the resistance to flow in pipe by blocking a portion of the pipe cross sectional area. And in case of turbines with high turbine solidity, in addition to rotational speed of the turbine can behave as an obstacle to water and thus would experience a high reduction in efficiency. And these graphs shows the turbine performance parameters with changing chord lengths. And for the study, he has, as explained earlier, he has chosen a chord length of 58 mm and 87 mm. And here we can see that the power gets improved with increase in chord length. The efficiency also gets improved, the torque gets more uniform, and as in the case of number of blades, the head loss gets increased with the increase in chord length of the turbine blades. And both the number of blades and chord length are significant contributors to the turbine solidity. However, there are practical limits to the number of helical blades, that is 5, and it is recommended that the solidity should not exceed 0.35. And previous results from the simulations showed that the effect of chord length is more pronounced in enhancing turbine performance than associated with the number of blades. The most important factors that the author has studied in his simulation, and the helical and for that the author has varied the helical angle from 0 to 60 and 120 degrees, and the results are shown in these graphs. From this graph we can see that although the straight lift based turbine has greater power compared to the helical turbines, but the head loss and the torque gets improved in case of a helical turbine, and adjusting the helicity from 60 to 120 degrees result in the reduction of power by 10.7, 16, and 28% at TSRs of 2, 3, and 4 respectively, which means that although the performance improves till increasing helicity from 0 to 60 degree, after which the performance gets reduced till 120 degrees. So it is unsuitable for increasing the helicity beyond 60 degrees, and as shown in the graphs the torque curves tends to be more stable until the minimum variation is reached at helicity of 120 degrees, and this is typically due to the characteristics of the NECA hydrofoil blades, which achieve their hydrodynamic maximum when flows is perpendicular to the blade section in straight bladed turbine. Studied the effects of pitch angle on the parameters of the turbine, and for that he has used a pitch angles of 0 degree, 3 degree, minus 3 degree, and minus 6 degree, and he found that the maximum power of 1350 watts and efficiency of 27% was achieved by the turbine when the pitch angle was at 0 degrees. At other pitch angles the power and efficiency significantly decreased, and this can be seen in the power versus pitch graphs as shown here. Also, the variation in blade pitch angle was found to have insignificant effect on the head losses across the turbine, and the highest torque that was produced by the turbine at zero pitch angle, and we can see this here in the graph between torque and the azimuth angle. It is the effect of hubs and shaft on the lift, drag, torque, and power of the turbines. And generally, hubs and shaft lead to an increase in the wake region of the turbine. So here in the CFD contours, we can see that the hubs and shaft have their own wake region, which influences the pressure distribution and velocity distribution near the blade. Generally, the wake of the shaft does not have a significant impact on the parameters of the blade, but the wake region of the upper and lower hubs leads to general reduction in the lift force in these blade sections, and these reductions can be shown in the graph here. We can clearly see that the overall drag force gets increased with taking into account the impact of hubs on the performance of these turbines. And here we can see the wake of these wake of the top hub at various tip speed ratios ranging from 2 to 4. So in all, we can conclude that the author analyzed the effect of various parameters on the performance of the Gaslov's helical lift-based turbine, and we can conclude that with the increase in number of blade, increase in the tip speed ratio, increase in the flow velocity of water led to an increase in the performance of the turbine, whereas the increase in the helicity of the turbine from 0 to 60 degree led to uh, more uniform torque, but after that from 60 to 120 degree the performance gets reduced, and the shaft and hub wakes lead to an increase in the drag force and reduction in the overall lift generated by the turbine, and hence a reduction in the performance. And we also looked at the pressure drop and the wake generated by the overall turbine. So uh, that's an end to the paper. Thank you. And after that, the author has just presented us with all the references of the study. Thank you.
Good morning. This is Parth Singh from the batch M3, roll number 2K20 ME 184. I have studied this research paper for the submission for my fluid systems assignment. The title of the research paper is Lift Type and Drag Type Hydro Turbines with Vertical Access for Power Generation from Water Pipelines. So, pipeline turbines are designed to supply power for smart sensors installed in water pipelines. There are two types of vertical access pipeline turbines considered in this research paper. That is a lift type runner and drag type runner. And the experimental tests and numerical simulations on the hydraulic performance of both of these turbines are conducted. The results show that both the lift type and drag type turbines can meet the performance requirements. Now coming to the introduction. So, to track hydraulic performances and water quality conditions along the water pipelines, numerous smart equipment such as sensors with remote data transmission are placed. But due to unfavorable site conditions, one of the difficulties of such powerful monitoring systems is their limited ability to keep the smart sensors with remote data transmission operating consistently and safely. In this study, two different types of pipeline hydro turbines with lift and drag type runners respectively have been created to supply the monitor system with power. The following conditions must be satisfied in order to ensure a regular water supply. The first, maintaining the original water flow direction. Second, having a straightforward structure that takes up little room and is simple to install. Third, not affecting the water quality. And fourth, having good startup ability at low flow rates and low pressure or at high flow rates. A pipeline turbine with high vertical axis may be best option to satisfy the aforementioned requirements. One is a lift type, that is Darius type, and the other is a drag type, also known as the Savonius turbine. The design of the lift type or the Darius type turbine can be seen in the labeled figure here, along with the parameters of turbine construction, that are the diameter, radius, rotor solidity, chord length, blade inclination, and the number of blades. The startup performance for the current pipeline turbine with lift type runner is a significant issue, since the flow rate is not very high and the blade attack angle is dynamically changing when the lift type pipeline is operating. The blade may dynamically stall, during which the blade characteristic curve has a ring-like form and a hysteresis phenomenon manifests itself. The dynamic stall is a complicated process that is accompanied by boundary layer separation, stall vortex production, development, and attenuation, as well as boundary layer reattachment. These processes have a significant impact on the turbine startup performance. Now coming to the drag type turbine, it is derived from the Savonius turbine which has constant diameter along the axial direction. The primary design parameters for the same are listed here. The pipe wall prevents the fluid from being discharged at zone 4 in figure 5 when the drag type runner is used in water pipeline. The levered blade's negative impact is amplified and the high pressure zone B is expanded. In order to lessen the negative impacts of the levered blade, several researchers have investigated utilizing a flow guiding device to guide the fluid to the windward blade. The entrance nozzle for a drag type hydroturbine has a similar effect as the flow guiding device's goal of directing the flow to the windward blades and increasing flow velocity by constricting the flow path. In this instance, a drag type turbine was equipped with an I-type deflector baffle that performs well. It should be noted that the space between the levered blade and the baffle is a prime location for the creation of large-scale vortices and a stagnant water area. According to figure 6, the deflector baffle is made up of a main baffle and a sub-baffle. The sub-baffle wraps the runner to prevent formation of large-scale vortices in the stagnant water area or the rear side of the main baffle. The baffle is used to control the flow and boost its velocity. In figure 8, the test bench layout is shown, where the pump, torque motor, pipeline turbine, and brake are connected along with three pressure sensors at important points in the pipe, and the uncertainties in the experimentation are calculated with the function U as displayed. Next, the problem was set up for computational fluid dynamics. Structural mesh was used in the outlet area, whereas unstructured mesh was used in the input section and the rotating zone. A finer mesh is needed close to the surface of the blades in the rotating zone, where the runner is situated, as depicted in figure 10. Due to the significant disparity between the length of the blade cord and the runner's total size, the mesh or lift type turbines need to be small enough to be both the blade leading edge and trailing edge. For unstable computation, the ANSYS CFX was utilized. The RNG K epsilon model was chosen due to its advantages in taking into account the rotation and swirl effects in the average flow because of the substantial rotation effects of the flow inside the pipeline turbine. For the convection term, a high precision difference scheme was utilized, and for the diffusion term, a second order difference scheme. The maximum number of iterations for each time step was set to 20, and the residual of 10 to the power minus 4 was chosen as the standard for determining when all the simulated variables had reached convergence. Now, coming to the results of the simulation and the experimental setup. First, let's start with the lift type turbine. It is noticed that the experimentation and simulated results do not align on certain parameters. This error may be due to the geometric simplification and the choice of the K epsilon model. However, the main characteristic of the simulated curves is consistent with the experimental results, and qualitative analysis can be conducted based on the simulation results. The rotation speed of the lift type runner is in the range of 200 to 700 rpm, and the maximum efficiency of the turbine at each flow rate is higher than 30%. And at two large flow rates of 1 meter per second and 1.29 meter per second, the highest efficiency is more than 40%. The startup characteristics can be described by dividing into 5 stages that span from the shaking runner with slow rotation to the runner passing the startup process and accelerating quickly to reach a steady operation. Now coming to the results for the drag type turbine. Here, the numerical simulations were done with a Reynolds number of 1.57 into 10 to the power 5. The rotation speed is much slower than that of the lift type turbine in each operational scenario. The output power has a peak value and does not have a breakpoint at any rotation speed, according to the shape of the power and efficiency curves. The drag type turbine has a reduced efficiency, which under all working circumstances does not surpass 20%. The drag type turbine's essential startup flow rate is 0.18 meter per second, a substantially lower value than the lift type turbines. Whether it is starting or halting, the drag type turbine is stable, and there is no significant shaking of the runner. Now coming to the conclusions of the study. Vertical axis turbines with both the lift type and drag type runner for micropower generation in water pipeline system were studied experimentally and numerically. The critical incoming flow velocity of the startup process for lift type turbine is larger than that of the drag type turbine, which can lead to a lower flow rate, and the starting process of the drag type turbine is more stable. In comparison to a drag type turbine, a lift type turbine has a higher speed ratio and output power. The lift type turbine will brake at a high incoming flow rate until it stops operating as the turbine load rises, whereas the drag type turbine has a substantially low braking flow rate. Overall, there is still potential for development in this field, but both the lift type turbine and the drag type turbine can generally cover the energy needs of the data remote transmission equipment in water pipeline system. The essential incoming flow rate required for the lift type turbine startup can be further reduced, and the process's stability can be improved. The range of the tip speed ratio for the drag type turbine can be further expanded, and the output power can be enhanced. Thank you.
Hello everyone, my name is Piyush Verma. My roll number is 2K20 ME 186. Today I am here to give summary on the research paper of improving the efficiency of Pelton wheel in micro hydropower plants. Micro hydropower plants are used for providing electricity in rural areas of southern Africa, which are not connected to the grid electrical supply. Micro hydropower plants are situated in the perennial rivers in these areas. Generally, Pelton and cross-flow turbines are commonly used in these plants as these turbines are cheaper to construct and require less specialization compared to other types of turbines. Currently, some NGOs are running these plants for communities in countries like Zimbabwe, Mozambique, etc. Most micro hydropower systems are not able to deliver their best possible power output due to suboptimal design and construction of their various components. Like the turbine has the lowest efficiency compared to the other components, turbine is main focus of this research. Improving the turbine efficiency provide the best chance of improving the overall efficiency. This research shows the main factors that affect efficiency of Pelton wheel turbines, which include the fabrication process, material used, the control of the water jet movement, and the flow rate, etc. Literature review. Introduction to micro hydropower system. The MHPS are very similar to that of conventional type of hydropower plants. The only main difference between them is of size. Some components of MHPS. elect electrical distribution lines, an intake or a wire, a head race, a 4-bay tank, a trash rack, a penstock, a powerhouse, a tail race, etc. The equation which is used is the actual power is equals to the density of water into the flow in the penstock pipe into the acceleration due to gravity into the total vertical drop from intake to turbine into the total efficiency. Here, the efficiency of various components of MHPS are given in the table, among which the efficiency of the Pelton turbine is lowest. Turbines. Turbines convert energy in the form of falling water into the rotating shaft power. The head available and the flow rate and the power required are the factor of selection of turbine. Here are some components of the turbines: the intake shaft, the water nozzle, runner, generator shaft, generator, exit valve, powerhouse. Pelton wheel turbine. The principle of Pelton wheel turbine is to convert the kinetic energy of a jet of water into the angular rotation of the buckets as the jet strikes. The high velocity jet of water emerging from a nozzle impinges on the buckets and set the wheel in the motion. The speed of rotation is determined by the flow rate and the velocity of water, and these are controlled by the spare valve. For best efficiency, the water leaving the buckets after striking should have little remaining kinetic energy. Having transferred most of its energy, hence the water must have just enough speed to move out from between the buckets and fall away under the gravity of wheel. Characteristics of individual Pelton wheel bucket which affect the turbine efficiency. The splitter ridge should be sharp and smooth so that it cleanly splits the jet into two halves. The force on the bucket comes from it catching the water and taking out as much of the water's momentum as it can. The more the water's momentum absorbed by each bucket, the better the turbine efficiency. The angle of the splitter ridge is set at right angles to the jet when the full cross section of the jet is hitting it. The remaining shape is designed such that it allows the free flow of water. As it is shown in figure number 2, the water should travel in U-shape, removing all the energy from the jet and leaving the water stationary in air, and then have it fall under its own weight into the tail race. Here it is discussed about the velocity, where Vj is the speed of jet and Vb is the speed of bucket, and for maximum efficiency Vj should be twice of Vb. Now we have the characteristics of the Pelton wheel runner that affect the turbine efficiency. Diameter of runner, number of jets, number of buckets of a runner, and method used to attach these buckets to a runner are the characteristics of the Pelton wheel runner. Small runner is more preferable at it reduces the cost. The number of buckets are usually kept between 18 to 20. Less number of buckets can cause water not being caught by the bucket, and more number of buckets can cause result reducing the speed of runner. Material which are used to make the Pelton wheel turbine buckets. The commonly used material are aluminium, copper alloys, grey cast iron, stainless steel and plastics. The control of flow rate for maximum Pelton wheel turbine efficiency. Control over flow rate is very essential for achieving maximum efficiency in different site conditions, as flow rate highly affects the efficiency of turbine. Now the efficiency is classified into hydraulic, mechanical, volumetric and overall efficiency. Power at inlet of a turbine is maximum and it gets reduced as water flows over the bucket due to the hydraulic loss. Due to the mechanical losses, the power is available at the shaft of the turbine is less than the power delivered to the runner of turbine. Some of the volume of the water is discharged to the tail race without striking the runner of the turbine, causing the volumetric losses. Now the overall efficiency is the ratio of power available at the shaft of the turbine to the power supplied by the water at the inlet of the turbine. Result analysis and discussion. Factor affecting the Pelton and cross-flow turbine efficiency. The head and the flow rates were collected from each of the 4 study sites. This data was used to calculate the gross power output. As it is given in this table number 2, the efficiency of the Pelton turbine is designated at 60%. The pattern of the single piece Pelton bucket as it is given in the figure number 3 was made after the studying the given table. Figure 4 shows the perfect alignment, number of buckets and the angle as well as the distance between the buckets providing no disturbance to each other. Figure number 5 shows the housing in which each panel is cut with cutting torch improving the accuracy. The effect of roughness due to the manufacturing processes. Each manufacturing process has different roughness. This combined with material roughness determining the friction of a turbine, and it will then translate to turbine efficiency, in particular hydraulic efficiency. The given table number 3 compares different manufacturing processes against the overall turbine efficiency associated with the manufacturing processes. Figure 6 shows a graph that relates this roughness to the turbine efficiencies. On x-axis we have the different method of manufacturing, and on y-axis we have the efficiencies. Blue line represent the turbine efficiency and red bar represent the roughness. Through this graph we came to know that the pressure dry casting turns out to be the best method for manufacturing. Effect of water jet movement. It turns out that to maximize efficiency, the jet must hit precisely the center of each Pelton bucket, which gives maximum drive to each bucket. Turbine material. Roughness, hardness and the cost are given in the following table number 4 for different material. Mostly the stainless steel is used for manufacturing turbine. Other material like aluminium, grey cast iron, brass, bronze and sheet metal can also be used for the manufacturing of turbines. Here, figure number 7 shows the material roughness compared to the material price. The blue bar shows the roughness and the blue line shows the price. According to the figure number 7, aluminium offers the least roughness and cast iron the most. Figure number 8 shows the material hardness compared to the material price, in which sheet metal has the highest hardness and aluminium has the lowest hardness. The two graph shows why stainless steel is the most commonly used material in the manufacturing of turbines for micro hybrid power plant system. It has high hardness, a very low roughness and price is close to the lowest. Sheet metal can also be used as is shown very similar properties as of stainless steel but its roughness is much higher than of stainless steel. Effect of increasing turbine efficiency on the micro hydro scheme power output. The two MHPs were analyzed further looking at the change that these turbines will bring in terms of power output. The change in the actual power output due to the increase in the turbine efficiency of the two MHPs that were studied is shown in the table number 5. In table number 5, the new efficiency for both of the MHPs turns out to be 85%, which is 25% increase in the efficiency. Conclusion and recommendation. Using the material and manufacturing processes that give the best highest yield possible from each site and resources is most ideal. The prices of the turbine in the quotation from supplied were such that the project costs remained within the budget. More electricity was generated, hence the cost per unit kilowatt actually decreases, making the project even more viable. Use of better efficiency turbines make it possible to harness more electrical power from the same resources. Thank you.
Myself Saksham Verma, 2K20 ME240. I'm here to present my views on the research article Performance Enhancement of Centrifugal Pump by minimizing casing losses using coating. The main abstract of this article is to focus on the experimental and numerical investigation of the effects of surface roughness of casing and adhesive coating on the efficiency of centrifugal pump. It basically consists of two parts. In the first part, effect of coating centrifugal pump casing by ultra smooth ceramic based coating on the efficiency of the centrifugal pump is investigated, and in second part, effect of change in surface roughness of casing is investigated numerically by using the CFD tool. Um, Introduction. The primary function of the centrifugal pump is to handle fluid from lower level to a higher level. The purpose of the and the use of these pumps are more extensive, which include domestic agriculture, surface water treatment, and distribution and wastewater treatment plant, oils and chemical industries. These pumps consume about 20% of the electrical energy which is produced around the globe. Now, many researchers have worked on the efficiency enhancement of centrifugal pump by investigating effects of the designs. And so, firstly, the basic laws which concerned the many researchers are the first is the hydraulic losses. Hydraulic loss are the major contributor to the performance deterioration of the centrifugal pump. Many recent investigators focus on hydraulic losses. Two prime mechanisms of hydraulic losses are skin friction due to the surface condition of various components and interfacial surface energy at solid liquid interface. Demonstrating the effect of smoothing several parts of centrifugal pump at low and high specific speed, it is observed that efficiency improvement of 5 to 18.5% can be achieved by partial smoothing of various parts. Smoothing the impeller, front shroud and back shroud is found very effective for efficiency enhancement. The influence of volute surface roughness on the performance of centrifugal pump was investigated earlier, and it was observed that volute surface roughness increased from 0.08 to 1.2 mm and pump maximum efficiency decreased by 7.5%. It is also noticed that no considerable effect of volute surface roughness is produced on the impeller flow field. Now, CFD has emerged as a very effective tool in handling various turbo machinery problems. Various researchers have modeled the centrifugal pump with different phase roughness in CFD to investigate the effect of the surface roughness on pump performance. In CFD analysis, there are two ways to analyze surface roughness. The first one is taking into account total surface shape, but the very fine mesh is required for such an approach. The second method is by defining surface roughness in terms of some special parameters. Sand grain equivalent parameter is used to define surface roughness in most of the parameters. Now, considering the effect of surface roughness of various parts of centrifugal pump on efficiency and recent advances in polymer technology, surface coating by polymer coating materials to reduce surface roughness is an effective way by enhancing the energy efficiency of the centrifugal pump. Now, the numerical approach. Firstly, a 3D flow simulation was performed on a geometric model of the pump using Reynolds average Navier-Stokes equation. For current study, full computational domain considered consists of three separate cell zones, that is impeller fluid, casing fluid and inlet pipe. In numerical analysis of complex geometries, computational time and accuracies of result are prime concern. Computational time can be decreased with generation of suitable grid without hampering accuracy of obtained results. In the present study, of four different grids are generated and most suitable grid considering elements count and accuracy of result is chosen. Now the here is the um, analysis of pump using ANSYS software. 3D flow dynamics in centrifugal pump are described by continuity equation and Reynolds average Navier-Stokes equation. And the table represented here determine the element numbers, head, deviation of head from experimental value, and efficiency and deviation of efficiency from experiment value are shown here. The figure here represents the pressure contour for 6.6 kg per second and 100 micrometer, 200 micrometer and 300 micrometer surface roughness respectively. And the same is for figure 3 and 4 uh, of pressure contour 6.6 and 5.95. Now experimental investigation for analyzing effect of coating. Experimental setup. Experimental setup consisting of two centrifugal pumps of identical rating, one without coating and with coating on casing, is developed by investigation of coating effect on efficiency. Layout of experimental setup is shown in the figure 10. Here is the figure. We show the curve of head versus flow rate diagram. Pump 2 is coated with ultra smooth ceramic filled adhesive material while pump 1 is uncoated. The used adhesive material was an ultra smooth ceramic reinforced epoxy that provides a high gloss, low frictional coating designed to protect against turbulence and abrasion under typical dry service temperature of -29 to 120 degrees Celsius. Readings are taken by varying head and recording corresponding changes in volume, flow rate of fluid and energy extracted by the pump. Here are the curves of head and discharge, and here is experimental versus numerical curve of discharge, and here is the experimental setup layout. Now experimental results. From experimental results, the relationship of head with volume flow rate of water and head with efficiency obtained for both coated and uncoated pump is shown in figure 11 and 12. Here are the figure. Figure 11 shows head versus discharge pump characteristic with coating and without coating. And figure 12 shows discharge pump versus efficiency with coating and without coating. And finally, the summary and conclusion of the research article. The study reveals effect of surface roughness of casing and centrifugal pump performance based on the numerical and experimental work. The following conclusions can be drawn. Firstly, surface roughness of casing has considerable effect on pump performance. Surface roughness of casing does not affect flow field impeller inside impeller zone considerably. Change in surface roughness from 100 to 300 micrometer result in head difference of 1.53 to 2.15 meter of water for different mass flow rate values. Effect of casing surface roughness is more severe at higher mass flow rate values, and surface coating of casing with ultra smooth ceramic filled coating results in efficiency enhancement of 2.11 to 9% for different volume flow rates. Thank you.
Hello everyone, my name is Parsun Kapurgiri. My roll number is 2K20ME183, and in this video I am going to talk about Pelton turbine. Okay, so Pelton turbine is an impulse turbine. It is a tangential flow turbine, high head turbine, low discharge turbine, and low specific speed. Minimum pressure in Pelton wheel turbine is equals to that of atmospheric pressure. Minimum pressure in Pelton wheel turbine is equals to that of atmospheric pressure. So if minimum pressure is that of atmospheric pressure, then there is no cavitation in the Pelton wheel turbine, and if there is no cavitation in the Pelton wheel turbine, then no draft tube is needed. And what is now the question is, what is cavitation? Cavitation is something which you can say that uh, formation of vapor bubble in the low pressure zone. You can see in this figure. Okay, before cavitation, let me explain about this figure. Okay, so you can see in this figure that from A to B, it is a converging portion, and from B to C, it is a diverging portion. Okay, so velocity the when jet enter into jet enter from A to B, their pressure decreases. Okay, and when jet enter from take exit from B to C, the pressure again increases. So from B to C, it is a high pressure zone, and this the diverging portion from B to the when you come from B to downward. Okay, so I have not mentioned the name of that point. Okay, so when at the area you can say near about B, it is a low pressure zone, and when from B to C, it is a high pressure zone, and these bubbles burst only in these high pressure zones. Okay, vapor burst and pressure wave is generated which travel to hit the wall, and it may damage the wall. So this process is only known as cavitation. Okay, so in Pelton wheel turbine there is no cavitation because minimum pressure is that of atmospheric pressure, and so the cavitation is also not there. So draft tube is also not required. Okay, cavitation is harmful for turbines because it is responsible for stress concentration, and if there is stress concentration, so the surface life of the vessel or surface life of anything will decreases. Okay, so major components of Pelton wheel turbine are nozzle and flow regulating arrangement, runner and blade. In other terms, you can say blades as buckets also. Okay, so I have attached the photo of the blade. You can see here, blade, or you can say bucket. Casing, braking jet. Now, what is the braking jet? Braking jet is used to stop the wheel. Okay, so there something is required to stop the wheel. So for that, braking jet is used. Okay, so braking jet is used. Okay, and now basically this is the basic introduction of the Pelton wheel turbine. Now what we have to discuss is Pelton wheel turbine is a high head turbine. Okay, so this high head turbine, how can we use it when the head is low? Okay, so there are many research papers about this. I have taken a research paper from International Journal of Engineering Research and Technology, volume 13, number 10, and the name of the research paper is a study to improve the efficiency and performance of a Pelton wheel turbine using potential energy at low head. It is published. This research paper is published by J.M. Havlenko, P.V. Saub, and A.A. Ablongo, Department of Mechanical Engineering, Faculty of Engineering and Technology, Weil University of Technology, South Africa. Okay, so in this research paper they have explained how the Pelton wheel turbine can also work at a low head and with using potential energy. Okay, so Pelton wheel turbine is basically a high head turbine, but with using potential energy we can use it at a low head also. Okay, so theoretical framework of the model using potential energy at low head. So this is the photo which I have attached. They have explained about this in their research paper, that in deriving the theoretical model for application to improve the efficiency and performance of a Pelton wheel using potential energy at low head, it is one of the major types of the turbines along with the reaction turbine. Impulse turbine operate based on the concept of velocity, namely by direction of a jet of either fluid or gas. This impulse in turn rotate the turbine and create energy. A turbine that is driven by the high velocity jet of water or steam from a nozzle directed onto vanes or bucket attached to a wheel. The resulting impulse, as described by Newton's second law of motion, spins the turbine and remove kinetic energy from the fluid flow. Before reaching the turbine, the fluid pressure head is changed to a velocity head by accelerating the fluid through a nozzle. This preparation of the fluid jet means that no pressure casement is needed around an impulse turbine. Okay, so this is the photograph for complete project diagram. Okay, so they have discussed about this in their research paper. Now let me talk about the working of a Pelton turbine. Before talking to working of Pelton turbine, let me discuss some basic things of Pelton turbine. A Pelton wheel turbine, a Pelton wheel is an impulse turbine that has at least one free jet. Okay, so in Pelton wheel, at least one jet is free. This jet releases water into aerated space where it caught by the series of buckets. So I have explained in the previous part what is bucket. Bucket is basically blade. Okay, so bucket or cups located on the runner, the rotating piece of the turbine that is used to convert the water energy into mechanical energy. Typically, these buckets are divided into two sections, so they are able to deflect water from the oncoming jet. A Pelton wheel also has a cutway on the lower lips of the bucket, which allow a subsequent bucket to move ahead before it stops the water jet that moved the previous bucket. As a result, the bucket enters the water jet more smoothly. So now let's quickly talk about the working principle of Pelton turbine. So Pelton turbine working principle: the water from the tank flow through a pipe. This pipe is from connected from the reservoir to the turbine. Okay, from the pipe which contain an orifice at the outlet. The nozzle escalates the kinetic energy of the penstroke. At the outlet, the nozzle produce a water jet. So you can see in this video how it works. Okay, so now how can we modify the Pelton wheel design so that it can work at a low head using potential energy? Pelton wheel is generally used for high head and low discharge application, but it can be used for a low head also by adding some modification in the design. The splitters are used to increase the efficiency of the outlet of the water jet so that water can leave the bucket with the minimum velocity, which is theoretically assumed tends to zero. The A special modification is to increase the depth of the bucket, which is not done in the usual Pelton wheel bucket. In case of conventional Pelton wheel, only kinetic energy of the jet impinged from the nozzle is used, but there is no application of gravity in the turbine action. In this gravitational low head Pelton wheel, both the kinetic and gravitational energy of the jets are used. The wheel of this stored water per second in the bucket is the amount of the potential energy per second from the water jet. Further, this potential energy is converted into kinetic energy as this water filled bucket freely falls. This is assumed that this freely falls. Okay, so it is also possible to extract kinetic energy from penstoke nozzle discharge by a mean of jet stroke through conventional Pelton wheel vents of the runner. This hydro system is good for a low head and a heavy discharge application. Okay, so you have seen that how we can modify the Pelton wheel turbine so that it can work at a low head also. Okay, so this was all about this research paper, and the references which are used in this research paper are as follow. I have attached the screenshot also, and I am telling it also that references which are used is from there are basically 12 references which are used. You can see in the research, you can see the screenshot which I have attached here. Okay, so that was all from my side, and in this basically a small video I have explained that how we can use what is Pelton wheel, and how we can use Pelton wheel is a high head turbine, but how we can use it a low head also using potential energy. And I have taken this from a research paper, and I have also stated the name of the research paper. And this was all from my side. Thank you very much.
Hello everyone, this is Pragya Ratan, roll number 2K20 ME187. Today I am giving you an analysis on the topic hydrodynamic converter, which is a patent given by Professor Reinhard Kerner on dated November 1, 2022, and the application number is given on the screen. So as we move further, we are going to discuss the hydrodynamic torque converter. So first the one question is arrived in our mind, that is, what is hydrodynamic torque converter? So a hydrodynamic torque converter such as hydrocoupling and torque converters are fluid couplings that typically uses oil as a process liquid to transmit power from an output shaft driver pump to an input shaft driven turbine. So as we can see this on the screen, hydrodynamic converter, a high-speed hydrodynamic adjustable converter having a working chamber for forming a hydrodynamic working medium circuit wherein a pump wheel, a turbine wheel and a guide wheel are positioned in the working chamber. The working medium flows through the pump wheel centrifugally or centrifugally diagonally, and the working medium flows through the turbine wheel centripetally or centripetally diagonally. The inlet grate edge of the turbine wheel with respect to an axis of rotation of the pump wheel and the turbine wheel is positioned on a smaller or equal radius than an inlet grate edge of the pump wheel. The hydrodynamic converter has a first guide wheel in the working chamber before the pump wheel viewed in the direction of flow of the working medium. The guide wheel being arranged for purely centrifugal or diagonal centrifugal through the flow of the working medium and is used to influence the power transmission. Now we are going to discuss the background of this invention. So first we are going to start with the field of invention. So the field of invention is this current invention relates to the hydrodynamic converter. Now the descriptions of the related are: a hydrodynamic converter of this type is disclosed wherein the working medium of the circulatory flow in the working chamber flows at least partially centrifugally through the pump wheel, wherein the working medium of the circulatory flow flows at least partially centrifugally through a guide wheel. In such cases, of the converter is also referred to as a guide vane ring because, in contrast to the pump wheel and the turbine wheel, it does not rotate, and where in the direction of flow, the working medium of the circulatory flow progresses onto the turbine wheel, parallel to the axis of rotation in axial direction of the hydrodynamic converter, whereas the outflow direction of the working medium of the circulatory flow out of an turbine wheel progressively, partially, centripetally, and partially in the axial direction, thus diagonally. Now, as we move further, another question arises in our mind, that is, how does a torque converter transmit the power? The torque converter casing connects to the flywheel spinning at the same rate as the crankshaft within the housing of the turbine. Here, the impeller or a centrifugal pump effectively flings the transmission fluid into the fins of the turbine, that in turn spins or transmits the torque into the transmission. Now, the summary of this invention. A hydrodynamic converter, according to the present invention, has a working chamber for forming a hydrodynamic working medium. However, another medium, for example water or a water mixture in a particular water glycol mixture, is also considered. At least one pump wheel, at least one turbine wheel, and at least one guide wheel are positioned in the working chamber, one after another in the direction of flow of the working medium. Viewed in the flow direction, a guide wheel generally flows the pump wheel and the turbine wheel follows the guide wheel. Moreover, an additional guide wheel can, for example, be provided in the flow direction before the pump wheel, wherein the guide wheel is in the advantageously adjustable. As we move further in the summary of this invention, now the second point comes. According to this present invention, the working medium flows through the pump wheel centrifugally in a particularly purely centrifugally or centrifugally diagonally, and the working medium flows through the turbine wheel centripetally, in particular purely centripetally or centripetally diagonally. So as we can see in this figure, on the left hand side, this is the engine from where the fluid will come, and now that fluid will come into the pump. This is having 29 blades, and then the stator having 22 blades, then turbine having 25 blades, and at last there is shell, and after all this the fluid will come at the gearbox. Now the hydrodynamic converter is preferably designed as a single step hydrodynamic converter with a single turbine wheel. In the second figure we can see the components of the hydrodynamic converter. Here the full blade passage model, pump, stator, turbine, and axis of rotation in the center, and the single blade passage model. So according to this, the present invention, a first guide wheel is provided. For example, the guide wheel that is adjustable around the axis of rotation, wherein the guide wheel is preferably arranged for a purely centrifugal or diagonally centrifugal flow with the working medium in the working chamber. According, the working medium flows centrifugally or partially centrifugally and the partially axially into the first guide wheel and centrifugally out of the first guide wheel. So the hydrodynamic converter is preferably speed limiting, that is at increasing speed of above the upper working region speed ratio. The turbine wheel ensures a breakdown in the circulating mass flow of the working medium and therewith the associated immediate attainment of the threshold point. In particular, hydrodynamic converter is itself speed limiting above a speed ratio of 3. So here on the screen we can see that the enlarged view or a cross-sectional view of the hydro turbine converter. Here the torque converter, this figure is basically the torque converter for an automatic transmission. So here we can see the notches in support shaft engage pump in transmission, transmission input shaft, automatic transmission fluid, ATF fills casing during operation, stator in the center, and just as we can see in the above figures, there is on the left side we have an engine crankshaft, and on the right shaft we have the fluid path caused by the centrifugal force of spinning torque converter. And these are the component identification list. In this we have pump wheel, turbine wheel, first guide wheel, second guide wheel, as follows to the fourth guide wheel, in which there is the axis of rotation at the 8 point and the inlet grate edge also. So now this is the basic, this is the main part of this patent, which is of hydrodynamic converter. So the claim number 1 is the hydrodynamic converter of claim 1, wherein the first guide wheel has an inlet grate edge which is relative to the axis of rotation, is positioned on the radius that substantially corresponds to the radius of the inlet grate edge of at least one turbine wheel. The hydrodynamic converter of claim 2, wherein the radius of the inlet grate edge of the first guide wheel is 0.8 times to the 1.2 times or 0.9 times to 1.1 times or 0.95 times to 1.05 times the radius of the inlet grate edge of at least one turbine wheel. The hydrodynamic converter of claim 1, wherein the first guide wheel is arranged immediately before at least one pump wheel viewed in the direction of flow of the working medium. The hydrodynamic converter of claim 1, wherein the at least one guide wheel further includes a second guide wheel provided in the working chamber, which is arranged for a purely axial or diagonal axial or axial diagonal throw flow of the working medium. Now the hydrodynamic converter of claim 7, wherein the second guide wheel has plurality of guide vanes which are arranged in two groups adjacent to one another behind one another in the working chamber. A number of guide vanes of the first group is smaller than the number of guide vanes of the second group. The hydrodynamic converter of claim 9, wherein the third guide wheel is positioned for a purely axial flow of the working medium. The hydrodynamic converter of claim 10, wherein the second guide wheel is positioned on the large diameter than the first guide wheel, and the third guide wheel is positioned on the smaller diameter than the first guide wheel. As follows. Now, the hydrodynamic converter of claim 1, wherein the radius of the inlet grade edge of pump wheel is 1.1 times to 1.3 times the radius of the inlet grade edge of the turbine. The hydrodynamic converter of claim 1, wherein the arrangement of the positioning of the pump wheel and the turbine wheel makes possible a speed ratio between the turbine wheel and the pump wheel speed in the range of 1.8 to 2.0, as well as working range of up to 2.3. So here we have done with our patent analysis work. So thank you everyone.
Hello everyone, my name is Paras Kumar and my roll number is 2K20 ME181. In this video, I'm going to tell you about design and analysis of Pelton wheel turbine. First of all, I'm going to tell you about the basics, definitions and components of Pelton wheel turbine. Pelton wheel turbine is type of impulse turbine which converts water energy into mechanical energy. And later this mechanical energy can be converted into electrical energy with the help of an electric alternator. Pelton wheel was invented by Lester Allen Pelton in the 1890s. Pelton wheel turbine is impulse turbine and it has tangential flow, and the turbine, the head of Pelton wheel turbine is high and it has low discharge turbine, and it has low specific speed. The minimum pressure of Pelton wheel turbine is atmospheric pressure. That's why it has no cavitation, and in this we don't have to use the draft tube. Inlet is only kinetic energy. And now some advantages of Pelton wheel turbine. Pelton wheel turbine has simple construction and it is easy to maintain. Intake and exhaust of water takes place at atmospheric pressure, hence no draft tube is needed. Overall efficiency is high and work on low discharge. And now some disadvantages of Pelton wheel turbine. It requires high head for operation. Turbine size is generally large. Its efficiency decreases quickly with time. Due to high speed, it is very difficult to control variation in operation head. Some basics. A Pelton wheel turbine is considered as an impulse turbine, as I tell you. A turbine that converts pressure head into velocity head. This thesis is to calculate input power, output power, buckets, speed ratio, and the length of the belt and efficiency of the turbine. The turbine with a jet diameter of 0.0254 meter has been designed for the operational conditions of the Pelton wheel installed at the Moni Tava cave, Etharia. Sorry for the pronunciation. The diameter of the runner is 0.25 meter, with the width of bucket is 0.1143 meter. The turbine has undergone efficiency testing and visual inspection during operations at a gross head of 20 meter. The hydraulic efficiency is 96.35% and the output power is 400 watt. Now, components of Pelton wheel turbine. The main components of Pelton wheel turbine are as follows. First is nozzle and flow regulate arrangement. Second is runner. Third is bucket. Fourth is casing. Fifth is penstock, and last one, sixth, is the jet of the water. Now, working principle of Pelton wheel turbine. The high speed water jets from the nozzle strike the buckets at splitter placed at the middle of a bucket, from where jets are divided into two equal streams. These streams flow along the inner curve of the bucket and leave it in the direction opposite to that of the incoming jet. The high speed water jets running the Pelton wheel turbine are obtained by expanding the high pressure water through the nozzles to the atmospheric pressures. The high pressure water can be obtained from any water situated at some height or streams of water flowing down the hills. The impulse generates the torque and rotation in the shaft of Pelton wheel. To obtain the optimum output from the Pelton wheel, the impulse received by the blade should be maximum. For that, change in momentum of the water stream should be maximum. If possible, that is obtained when the water stream is deflected in the direction opposite to which it strikes the bucket and with the same speed relative to the bucket. Now, for a constant flow of rate from the nozzle, the high-speed turbine changes with changing loads on it. For quality hydroelectricity generation, the turbine should rotate at a constant speed. To keep the speed constant despite the changing loads on the turbine, flow rate through the nozzle is changed. To control the gradual changes in load, servo control sphere valves are used in the jets to change the flow rate. And for sudden reduction in load, the jets are deflected using deflector blades so that the sum of the water from the jets does not strike the blades. This prevents overspeeding of the turbine. Now, the hydraulic turbine is one of the most important parts to generate electricity. In this thesis, different types of hydraulic turbines are briefly discussed and three types of impulse turbine are described. Peltel vane is generally used as a powerful mechanical device. Head is the most important in the Peltel turbine. In this thesis, the cross head and diameter of the jet are 20 meter and 0.0254 meter. The wheel with a pitch or diameter of 0.254 meter has been designed for operational conditions. Of the radial length of buckets is 0.0635 meter and the depth of bucket is 0.3 meter. The velocity of the jet is 19.412 meter per second and velocity of bucket is 8.914 meter per second. As Pelton wheel design is easy and easy to construct, this wheel can be manufactured by any simple workshops having facilities to weld, drill and cutting. The Pelton wheel turbine can be used for more than 50 meter head of water and it can be built with local material and the cost is low. Then the Pelton wheel has high speed and the speed can be raised by means of gearbox or pulley. Thank you. And in last, I took some references from Fluid Mechanics, Hydraulics and Hydraulic Machine by Dr. K.R. Arora. Thank you and have a nice day.
Hello sir, this side Parveen Prajapati 2K20 ME 185. My topic is Francing turbine and method of operating same. Francing turbine. Sir, in this, basically, Francing turbine includes a waterway. In this, distributor approaches disposal in the waterway and an additional element for adjusting the flow of water through the turbine. We use the adjacent element, and we're going to study about that after. And we use the different type of like metal seed, ring, and other type of plate type method. And there we use the different types of methods also and Francing turbine, including a water bay. So here we can see that is a water turbine where water inlet and outlet always happen. There we uses the different type of method to make better, and where we can use plates also. And that whatever the stuff we have looked at before, we gonna make that better, and that is the here invention that also happen. And in that we using the different type of stuffs like metal sheets, plates to make them better. And after that we discovered that. And so here we can see some kind of invention we have seen in this invention related to a Francing turbine and a method of operation that sir always happen. And this is also known as priority queue. And sir, like we mass flow and inclined angle in this to blade angle will be regulated. And in this we put it two parameter also adjacent to make adjacent comfortable. And so we can see that the design point is characterized by efficiency use. Means as much efficiency gonna best, our invention gonna more efficient, more perfectly. And after that, DE proposed a double regulated Francing turbine, which according to double regular pressure of its range between 50 to 150 meter. That is totally good. But according to there is also some kind of a drawback also. And as a solution is given by the themselves, that is efficiently turbine high maybe adjacently, and distributor approaches has an adjacent upper rim. And after that, as we can see, there is some drawback too here. So in that that is like we can see in the picture, that is totally a very complexity and high demandable and highly costable. And we need like a maximum area to cover that. That is the totally drawbacks about here. And after that, I just summarize about their inventions. Sir, in this invention is that to provide higher efficiency of the designing and conventional Francing turbine. And sir, according to the invention and disposal in the water way, and additionally element for the flow of water through the turbine water, and element water goes to upstream, that is totally up that as water goes to upstream and pressure gonna high, or pressure gonna high there. And this is also in resulted by the D through the D. And after that, we just look up here, sir. In here we can see turbine efficiency graph. So we just look at here, like there is a 0.97, like that is we just cover everything, we make the graph there, like how much it's gonna be effectively, how is efficiency gonna increase. Like 0.9 is gonna one, that is totally good for us. And after that, that graph is gonna decrease in one time, it's gonna increase, and that's gonna totally graph increasing and increasing, that is totally good for it. And after that, there is some claims also, sir, we have just seen. And here is the first one claim is, in this water flow, sir, as a directly defined and implicit disposal is waterway, and sir, an additionally element for adjacent a flow, and sir, of water through the Francis turbine set additionally element begin disposal. And after that, sir, we use the metal sheet having a different type of, as we discuss about the ring and plate type, that is metal we use to make them better for future. And here we can see, we use the different type of whatever the metals and additionally element which is used, we use the in different type of stages. In one first stage additionally element we uses, and after that we uses the in first way we additionally slots, we uses the less width, and after that we uses the highest width, and after that we in third slot we just covering the width of the lesser of both of the faces, and metals is intended to enter set water. That's whatever we have using, whatever we have done in the three type of slots. And after that, sir, as you can see second France turbine, as we can see here that the Francis turbine according to claim metal sheet is flatted. So in that second case we just uses the flatted, that is good. And after that we uses the metal sheet as a ring type in the third one, and we uses the additionally integrated ring. And after that, sir, metal sheet is disposes concordiously. And after that, as we can see, there is maybe I just observe of everything that is good. And after we just look at about this, there is some kind of operations also happens on the Francing turbine, that in we just represent enough step by step. And here we can see that it provide water flow in definite direction, that is good. And in that Francing turbine, and an element for adjacent a flow of water, and water flow through the Francing turbine. And after that, and as we can see, sir, determining hydraulic fluids, and hydraulic fluids, that is also good. Their hydraulic fluid as hydraulic fluid is gonna decreasing their temperature and the pressure gonna always that is basically related to the pressure related to the power of the Francing turbine during the regulation scheme. And after that regulation carried out, and sir, selecting one set regularly scheme based on associated hydraulic losses. And after that, sir, we using additionally element to adjacent flow of a water through the Francis turbine, and to make them better. And as we can see that they are like in a graph, we gonna increasing downward then upward, from the starting to backward. We're using different type of plates there in slots form, and we using the in different type of width in both the cases, end to end. We use the slot, we use the for making the pressure better, and make the 50 to 150 width which is covered in a, to make them better in make that better in a particular way. That's all about me, sir. And after that, thank you so much, sir. Thank you so much. Thank you so much, sir. Thank you.
Hello everyone, my name is Elon Elias Jean. I'm in roll number 65. I will be talking about the fluid machinery. So I pick the topic of design of a single stage centrifugal pump. This topic will be discussed based on one research paper that was published in March 2022 by 5 authors, including Alumini Andreu Tawojo. So Centrifugal pumping, as we know, is have to be designed to get best performance as possible. Centrifugal pumping is chosen to be a most versatile rotodynamic equipment in the fluid operation that have a wide application as residential, we have a agriculture application and also industrial application. So as a result, the design of parameters, operation circumstances, and the maximum efficiency with the less amount of consumption of power is required to be determined. So in this experiment or research paper, we will be studying particle centrifugal pumping, impeller, flow rate, and the head of it, the centrifugal pump, because these are the most important thing that we should keep in mind when we are designing and building one centrifugal pump in order to have a better performance as possible. So I told you before, centrifugal pump are commonly utilized to move the water across short to medium distance via pipelines with the modest head and the discharge requirement. So the goal of having this project is to improve the performance of the centrifugal pump by modifying an impeller. So in this research paper, specifically we are trying to modify the impeller in order to have a best performance in centrifugal pump. Yes, as we know, we have a different kind of impeller. So it's we need the best impeller must be chosen according what we need. So we know that the best performance is determined by the cost, by the necessity of the requirement, and the another other aspect that we will be discussing in this topic. So how we know impeller imparts centrifugal forces to produce fluids, while a diffuser is the permanent element that directs the flow of discharge in centrifugal pumps. Shape of the impeller impacts on the pump's performance. As I told you before, the shape will impact in the pump's performance. So the impeller must be determined to improve the performance. So the important factor with pump designers put in consideration during design is to avoid failure during the service is cavitation. So cavitation is something that we must try to avoid. So cavitation results in vapor or bubble formation in fluids due to pressure reduction below that of this vapor pressure. Cavitation is caused by the decrease of suction pressure, a rise of suction temperature, or a flow rate greater than that for which the pump was designed. So to avoid this cavitation, to prevent this cavitation, we need to put in mind that the fluid pressure must maintain above saturation pressure through the pump, and the net positive suction head is a measurement used to see if the pressure of the liquid being pushed is sufficient to avoid cavitation. So after all, we need to understand the importance of avoid cavitation in the centrifugal pumps. So when we are designing centrifugal pump, in this research paper, basically we are using one experiment that we will be given the value of the head, we will be having value of the head, we will be having a pump speed, we will be having the volume of the reservoir, and the time of the reservoir to the pump. So all requirement will be here. So to understand what should be the design of the centrifugal pump, we need to do some calculations to understand what will be the better performance of our pump. We need to calculate the flow rate of the pump. We need to understand what will be the shaft power, electrical motor power consumption, motor generating capacity, motor speed, and also we need to understand the requirement, the efficiency required. In this experiment, in this research paper, basically we will require the efficiency to be around the 80%. Okay. So also we need to understand the power output required to the pump. We need to understand the pump shaft diameter also, and the impeller eye diameter, velocity of inlet, as well inlet width, as well outlet. Okay, those all things you must be understood but to have a centrifugal pump. After having this calculation, we will understand the dimension required to build this specific centrifugal pump. We will be designing the valute casting, and after designing valute casting, we will be designing discharge flange, and after also the design discharge flight, we will be ready to complete our centrifugal pump, because we know what should be the rate flow, what will be the head, what will be the speed, the power, the consumption. All those factors will be joined to analyze if the centrifugal pump will be operating in best performance as possible. In this research paper specifically has a result, it has a conclusion. We note down that the many varieties of the pumps that are available, proper design is the most important requirement for any facility. General ensuring that the absence of cavitation and the proper flow. A single stage centrifugal pump design is analyzed in this paper. The numerical relationship between head, flow rate, rotation speed, and power has been successfully achieved. So all this requirement is achieved. So the pump can be considered as a viable option for the different pumps required in application like home and stores or etc. This project is designed, or the research paper and project is designed to have a much economical and will be helpful to obtain variable rate of discharge in a variable speed when fabricated and tested in a further research. So with those all aspects, we are now able to have a centrifugal pump, because how I say, the impeller must be adjustable to the requirement, because the impeller is the device who will move the flow, who will move the fluid, will move from the fluid, will give the pressure to the fluid. So the impeller must be designed in order to achieve a best efficiency. Okay, that's all about the centrifugal pump, a single stage centrifugal pump design. Thank you.
Hello everyone. Namaste, namaskar. My name is Fatih Sururi. I'm role number 91. So today we'll try to explain about some work, about some research. We'll focus about patents and summary of research paper. But I have already selected my paper, my research, my patents. I will discuss about a new system through the acceleration of the airflow in wind turbine. Firstly, what means a wind turbine? A wind turbine is a device that converts kinetic energy of wind into electrical energy. So we focus about the performance. How can I improve the performance in wind turbine? So uh, we'll explain here about different device, different application, different method developed in the five last year. So we discuss the abstract. This pattern is based on the wind industrial technology called diffuser augmented wind turbine (DAWT). So this technology consists of horizontal axis wind turbine, which is housed inside a duct with diverging suction on the direction of the free air stream. In this paper, a review of preceding patents related to this technology is carried out. Second, what is the objective of this machine? The objective of this application. So this paper present in innovative patents to improve the performance of horizontal axis wind turbine. In particular, this system is aimed at improving the performance of those turbines that otherwise might not be installed due to the low wind resource existing at certain location. Third, we develop the different method. The different method developed by the different scientists. The most innovative element of these patents are the semi-spherical grooves which are mechanized on the surface of two diffusers in order to guarantee a more energetic boundary layer. The coaxial diffuser, each is located downwind, downwind following the fast diffuser in order to increase the suction effect on on the air mass closest to the inlet. Third, the coaxial ring located around the diffuser, the first diffuser outlet, which are used to deflect the external airflow toward the turbine wakes. And we have fourth is the self-oriented system to oriented the system by prevailing wind direction. So before discuss about the direction about the result, it's necessary to about explain for the numerical simulation and the description of the patent device. So the patent is an innovative solution. It is an innovative solution on the field of the renewable energy and at improving the performance of the augmented wind turbine system. The way the air flow through the turbine is increased. Increasing is based on the following strategy: guiding in higher speed channel toward the turbine wake, delay on the separation point of the boundary layer following on the diffuser inner surface, and reduction of the pressure on the air region closer to the diffuser outlet. So the patented system will here describe satisfy the following requirements. It must be capable of housing a horizontal axis direct turbine. It must be self. It must be self orientation in order to position the turbine rotor on the direction perpendicular to the main wind direction. Thus allow the collection of the higher amount of energy every moment. So we have different applications, but it's better to give the result of our research. It is not our research, just the research made by other persons. So this application of patents increase the power generated. The power generated by a horizontal axis wind turbine with a three blade. We know we have three blade is presented. But the patent is designed and its performance is evaluated by using CFD. We know what means CFD, com- computational fluid dynamics. So the numerical results show that the system rise the airflow going through the rotor of the turbine. Okay, and the conclusion: the printing device in original contribution M is enable more profitable installation. Wind a turbine is placed where the wind resource is insufficient because the wind shear caused both by approximately of the earth and obstacle on the earth surfaces. So we have many simulation, numerical simulation. We have already explained about the description of this machine, this new machine, and we have also the numerical analysis. Will use CFD, and finally, we have the conclusion that the patent device aimed at improving the performance of horizontal axis wind tapping by means it is an airflow accelerator system based on the diffuser technology has been analyzed. This wind system is particularly suitable for location such as in urban environments where the wind resource is rather low. It's very low data. That's according to the result of the numerical simulation. The wind system is able to increase the airflow velocity in the region the closest to the fast diffuser, the closest to the fast diffuser inlet. So the airflow gained through the turbine rotor is achieved by generating a region of sub-atmospheric pressure within the diffuser. To do this, a different technique have been used, such as the brim or the gap between two diffuser, and the semi-spherical grooves mechanism on the diffuser surfaces also help to intensify the effect. Thank you so much. Good night.